Okay.
Alrighty, well, welcome everyone. Sorry, we can start. So you heard me before, so if you have Dr. Altamos's class, your exam 2 is next Wednesday. So this is like your last review session with me before, like in person. Before that exam, I did put in that group me. If you wanted, like, I'm thinking about doing a Zoom review session. So it'll probably be Monday or Tuesday. I think right now Monday is the winner for that. I would do it Sunday, but it's Easter Sunday, so I'll give y'all time to just not do that. So probably Monday night Zoom review, maybe 7 o'clock for like an hour, hour and a half or so. And you can just come and ask any questions beforehand. That'll be recorded and posted for both classes. And then if you have Dr. Altman's class, your exam 2 is Thursday. So, right, you have one more review session before then to ask any last minute questions, but you can also attend that Zoom link or Zoom session. It should be on both announcements and Canvas's pages. With that, I think it's also going to be chapters 5 through 8. You might cover a little bit of material, like if you're Dr. Altman's class, you'll cover material tomorrow that'll definitely be on your exam 2. You might cover a little bit of something on Tuesday, but both of them will give you clear instructions on what material is covered. I think both exam preview pages are available. And I think a mock exam should be released soon for both classes. Any questions for me before we get started? Okay, cool. With that, what questions do we have? What do you want to see? Yeah.
Can you do like a refresher of chapter 5?
Yes. I remind myself what chapter 5 is. They all blend in together at one point. Okay, chapter 5 was gases. Okay, so chapter 5 was So chapter 5 was your gas laws. Oh. Alrighty, so chapter 5 was gases. So this includes your gas laws and then a couple other formulas. So when we think of gases, what are we thinking of usually? Maybe names, equations, what do we think of? Pivner, awesome. All right, so we have PV is equal to nRT. What do we call this? Yep, your ideal gas law. Oops. Let's see. Right, so this is your ideal gas law. We have P is equal to pressure, and what unit is pressure usually in for ideal gas law? Atmospheres. What about V? Yep, it's volume and it's going to be liters. What is N? That's going to be your moles. What is R here? It's a constant, and what constant are we using? You don't need to know the exact value, but is it the big one or the small one? It's the small one. Right, both our values, your universal gas constant will be given to you on your exam sheet. So you just need to make sure you know which one to use. We look at our units for R here, it's in liters times atmosphere over mole Kelvin. And we see that we're using liters and atmospheres for our pressure and volume on the opposite sides. That's how it's going to match up there. The larger value is in joules. So that's more of an energy component. And we're not going to be using that for this R. And what is T in? Temperature in what unit? Awesome. Do you have to use Kelvin? Yeah, you have to use Kelvin, right? For some of your things, you are able to get away with using Celsius. This one, you must be using Kelvin. If you're given a Celsius, make sure you always convert this one to Kelvin. Any questions on the ideal gas law? Okay, what other equations or things do we think about when we talk about gases? Yep, we can have density. That kind of goes into play with the ideal gas law. What is the units for, or what's your formula for density? Mass over volume. Okay, it's gonna be mass over volume. And playing into this, right, we do know molar mass. Is going to be grams or mass in grams over moles. So we can interchange, right? And we can rearrange Pivner to include density and molar mass, depending on if we can solve for mass in one equation and plug that in and move it around and whatnot. Okay, but if you just know PV is equal to nRT, that's going to be the most important here. What are some characteristics of gases? Do we like gases to be at high temperatures or low temperatures? If we're talking about an ideal gas, right? We're saying that this gas is behaving like ideally. Is that gonna be at a high temperature or a low temperature? Why we say high temperatures? Perfect, right? Because what do we know? Kinetic energy is related to temperature. So as your kinetic energy goes up, your temperature is going up. They are directly related. All right, so as temperature increases, kinetic energy increases, and as kinetic energy increases, the molecules are moving faster, right? So the faster your molecules are moving, or the more kinetic energy they have, the higher that temperature, the more gas-like they're going to be. Right? If you want to take your pot of water and you want to turn it, you want to make it start boiling, do you turn your stove on or do you turn your stove off? You turn it on, right? You crank up the heat. The heat's going to heat up your particles and it becomes more gas-like. So at those higher temperatures, your gases behave more ideal. So at high temps, gases behave ideal. Me? 2 L's, 1 L? I don't know. You get the idea. Right? They behave like an ideal gas at high temperatures. What about pressures? Do we want high pressures or low pressures? We want low pressures, right? The lower the pressure, the more they're able to expand. And then along that same line, do we want high volumes or low volumes? We want high volumes, right? They want to be able to take up a lot of space. This room is very good for ideal behavior because there's a lot of space involved, right? So we want low pressures and we want high volumes. Right? At these conditions, high temp, high volume, low pressure, we're going to be having ideal gases. So you have a question saying, right, which one's going to behave the most ideally? You want your highest temperature, you want your highest volume, you want your lowest pressure. Any questions on ideal gas behavior? Does that make sense why we want those type of conditions? Any other equations that are usually involved with gases that anyone could think of? Like partial pressure? Yeah, perfect. Right, so we have the partial pressure of our gases. There's a couple equations that go along with partial pressure. Does anyone know one of them? Related. Ish. Right, so we're talking about a combination of gases. We're saying that if we have a combination of gases, we can have a total pressure that all of those gases are exuding. And that's going to be the combination of the pressure of gas A plus the pressure of gas B plus the pressure of gas C and so on and so forth, right? So partial pressure is just saying a sum of the parts equals the whole. That's one version of partial pressure. The other one is related to mole fraction. And that's saying that the pressure of gas A divided by the pressure of the total gas is related to the number of moles of gas A over the total moles. And this is related to the mole fraction, or that fancy X of gas A. Can mole fractions be negative? No, right? Your mole fractions cannot be negative. What do they have to add up to? They have to add up to 1. And I believe that's it in terms of conditions for mole fraction. Yeah.
Yeah, can you repeat one more time what those each variable mean that?
Yep, so for like PA, that's gonna mean the pressure of gas A divided by the total pressure of the system, right? PT. So PT is the total pressure, and then PA is the pressure for that specific gas. That can be, if you have three of them, that can be any of the three gases that you have.
And XA?
And then XA is going to be the mole fraction. So, right, you're gonna get a decimal for the PA over PT and or the NA over NT. And so that'll be that X value or that fancy X. And that gives you the mole fraction, and that's what can't be negative, and that's what has to, like, the sum of all of those has to add up to 1. Yep. Any other questions on gases? Any other equations with gases? All right, we talked about our ideal gas law, which is PV is equal to nRT. But remember, right, Boyle's law, Charles' law, those are all related in pressure, or PV is equal to nRT. They're just broken down into specific ones when you talk about them individually. I'm scrolling through all this stuff to make sure. Oh yeah. I think this is going to be given to you, but your right, your velocity, your root mean squared, is going to be your radical 3 RT over molar mass. And so what does this tell you? What does this equation tell you? Yep, and this is going to be the speed of your molecule. So what does MM stand for here? This is your molar mass. So if that's in the denominator, if something is getting heavier, is that going to move slower or faster than something that's lighter? It'll move slower, right? So this is saying that the heavier the molecule, the slower it moves. Right, so oxygen is going to be moving a lot slower. Oxygen gas can be moving a lot slower than hydrogen gas. I believe that's like the main idea behind gas, or chapter 5 and your gases.
What's the equation?
Yes, yep. So that's related to this VRMS here, right? So your velocity root mean squared is considered a rate, right? Velocity is a rate. So you can say rate 1 over rate 2 is equal to molar mass 2 over molar mass 1. I do believe this one is given to you. But this is talking about effusion or diffusion of something, right? So that of a gas, right, through a small hole in a balloon or something. Right, this will tell you that if you know the rate of one of the gases that's escaping, then, and you know which both gases you have, right? Oxygen and nitrogen, say, right? Then you can take those molar masses and compare them and find the rate of the other one. So related back to velocity, but just a different version of it. Yep, great question. Do you want to take a couple of practice questions on gases? Yeah. close enough. Alrighty, so we have this first question here. We have labeled the following graph with the gases below. Do you want to label each of them to H2, O2, F2, and Cl2? And we'll label them A, B, C, D. So what is this question utilizing? Or does anyone know what this graph is called first? It does start with the B. Yep, so this is one of your Boltzmann distributions. There are like two ways that you can show Boltzmann distributions. I've shown you one way here, where we're comparing different molecules at the same temperature. So what does this utilize?
Previous equation?
It's related to one of the previous equations we talked about. Yep, it's talking about VRMS. So we're looking at the rates of of a molecule. So what's different between all of these molecules? How heavy they are, right? The mass of them. So which one is going to be the fastest? The one that's really spiky or the one that's really spread out? Really spread out, right? The smallest one, the one that's moving the fastest, is going to have that nice spread distribution, because the molecular speed, that average, is going to be the highest out of all of them. So which one's going to be distribution D here? It'll be H2, right? That is our lightest. What's our heaviest? Cl2. So that one's going to be what distribution? It'll be A. Okay, one really good thing about like a fill in the blank or multiple choice question like this is that you have two extremes. You have A and you have D. So make sure that you take your two extremes, your highest and your lowest, and put those at the extremes. In this case, the more spread out is going to be your lightest one. And then the most peak-like is going to be your heaviest one. What is heavier, oxygen or fluorine? Fluorine, so is that going to be B or C? That'll be B. And oxygen will be C. The other version of this question is with you have the same molecules. So let's say we just take oxygen, but we put it at various temperatures, right? So we have one at 25 degrees Celsius, one at 250 degrees Celsius, and one at 500 degrees Celsius. If we have the highest temperature out of all of that system, is it going to be the A distribution or the D distribution? It would be the D, right? The fastest and the most hot, the highest temperature, is going to be your most spread out distribution in your Boltzmann distribution. Any questions on this one? It's a good like matching type of question. Okay. We'll do one more gas practice. Alrighty, so for this one, we have a sample of gas at 35 degrees Celsius, has a pressure of 745 millimeters of mercury. What volume does the gas occupy if 1.50 moles of the gas is present? And it's giving you a conversion factor. Do you want to try this one on our own? We'll reconvene in a couple minutes. Great. Yep.
Would they normally give us a conversion factor?
It'll probably be on like your formula sheet. Bless you. You get an answer. We're either both right or both wrong. So. Alrighty. Someone want to tell me how they did their question? Yep. So we're using Pivnert here. What do we need? Or if what we're given, do we need to change anything or can we use it directly? Awesome, right? So our temperature, we need to change from Celsius to Kelvin. So we're going to add 35 to 273. So we get 308. And do we need to change anything else? Awesome, right? So we need to convert our pressure unit from millimeters of mercury to atmospheres. So we have 745 millimeters of mercury. 1 ATM is 760. So we end up with 0.98. Pretty close to 1. Now are we good? I think so. Right, we're solving for volume, so we can convert Pivnert to volume is equal to nRT divided by P. We have 1.50 moles. We have 0.08206. And we have temperature. And we're going to divide by 0.98. And so I get a volume of 38.4 7 liters. Any questions on how we use Pivner? Okay, so a couple ways that they could make this maybe a little bit harder if they wanted to ask it as a short answer question. Right, you're given moles and you're given an unknown of the gas given. They could have you do some sort of limiting reagent question to find out how many grams are produced. And then you can use that many grams of the gas that you know to convert to moles that you can then plug into this equation, right? That's a pretty good question. They could give you partial pressure of something, right? And so you have to find the partial pressure of the gas and then plug it into Pivner here. Or, right, they could go the opposite, and then you could be given, right, you have to find the number of moles of your sample that you have, convert that to grams, and then use that in a reaction somehow, and find something else from there as well. Okay, so a lot of ways you can branch off from here. There's plenty of practice questions online, and then you'll get your practice exam. You can kind of see the difference of what they're going to ask you there. Those are a couple different ways that they could ask a slightly harder PV equals nRT question. Feel better about gases? Is that good? Ready, what other questions do we have? Yep.
Does it go over like loose dot structures or like resonance?
Yeah, absolutely. So just like how you would draw them or like what they mean?
Like, so I, for example, get confused on like, when they ask you for resonance, like, I don't know, to
Like,
be honest, I'm just trying to like, get better for the quiz. If there's like any other questions that would come in, like those chapters.
I did an example. Okay, so if we're given, we want to draw the Lewis dot structure.
Chapter would this be?
This would be chapter 7. Okay, so I want to draw the Lewis structure for CO3 2 minus. So what would be our first step in trying to solve a Lewis structure? Yep, perfect, right? We want to count our valence electrons. So if we are going to count our valence electrons for CO3 2 minus, how many valence electrons does carbon have? It has 4, yep. How many does oxygen have? Now that's 6, yep. How many of those do we have? We have 3. And then is that all our valence electrons? Good, we have a 2 minus on our ions. That means we need 2 extra electrons. So we'll have 4 plus 18 plus 2, and we end up with 24 valence electrons. What's our second step in drawing a Lewis structure? Good, and what's going to be our central atom here? Perfect. Right, so, carbon is going to be our central atom. It is our least electronegative, and there's also only one of them. Right, so if you have something that's only one, then, right, and then we have two elements, you only have one of one, and then multiple of the other. That's pretty easy. Your least amount is going to go in the center. But if you have, right, like HCN, all of those have 1, your least electronegative is going to be in the center, and it will never be hydrogen. Hydrogen will never be your central atom. But in this case, we do only have 1 carbon, and so carbon will be our central atom. What is step 3? Yep, right, so we're going to determine our central atom, and at the same time, We're gonna draw the skeletal structure. Right, so we put our oxygens as our terminal atoms. And now we need to count electrons used. How many atoms do we use per bond? 2. So how many electrons did we use when we did our skeletal structure? We used 6. So how many are left over? We have 18 valence electrons. Where did those valence electrons go? Good, we go outside to our terminal atoms. And that's going to be completing the octet for terminal atoms. How many electrons did we use for our terminal atoms? We used 18. So we have 0 left over. Is this our structure? Why? Good. Carbon, our central atom, is not obeying the octet rule. So what do we do if it's not obeying the octet rule? We're going to make a double bond. So that can be from any of our oxygens that we have here because they all look the same. So I'll take this one and we'll make it a double bond. So now we end up with our structure looking like this with the carbon oxygen bond having 2 single bonds and 1 double bond. Is this our structure?
Charges too.
Good, we can add our charges. And where did those charges come from? What did we calculate in order to get those charges?
Valence electrons minus the lone pair amount of electrons in the pairs minus 1/2 the bonds.
Perfect, right? And so that's going to be our formal charge. So our formal charge, we'll call this oxygen 1, 2, 3. Our formal charge on oxygen 1, I guess formal charge in general, is just your valence electrons minus number of lone pairs, or your unbonded electrons, minus 1/2 bonded electrons. So I'll write this different. This is number of right. This can also be valence electrons minus the dots minus the lines. Is a great way to remember that as well. So your formal charge on oxygen 1, how many valence electrons does oxygen usually have? It has 6. How many bonded, I'm sorry, this is not bonded. How many non-bonded electrons does it have? It has 6, and it has 1/2 of how many bonded electrons? 2, right? 1/2 times the 2 bonded electrons from that single bond. So we end up with formal charge of oxygen 1 as -1. And so that's where your charge comes into play. That looks exactly the same as oxygen 2 in the right-hand corner. This one also becomes a negative. What's the formal charge on oxygen 3 with the double bond? It's 0, right? It has 6 valence electrons. There are 4 non-bonded electrons, and there's 4 bonded electrons. We take half of those, that's 2. So end up with a formal charge of 0. Is this our final structure for CO3 2 minus? What's the second one?
This one here.
Awesome, perfect, right? So this is a potential structure for CO3 2 minus. But because we can move that oxygen double bond to two other oxygens, what does this molecule or ion have? Or exhibit? It exhibits resonance structure, and it has resonance, right? So we can take our double bond and we can move that to the top oxygen. Or we can move it to the rightmost oxygen. So how many total resonance structures are there for CO3 2 minus? There's 3, yes. So, great question. So we did formal charge for oxygen. If you have a neutral atom, it's just, right, maybe it's just CO2. You want to make sure that your formal charges on each of your atoms are minimized, as in the most have 0, right? You don't want one having a +1 and a -1. You want them all to be 0 if possible. In our case, we're given CO3 2 minus. So that means that some atom has to have some sort of charge because our formal charges need to add up to that charge that's on our ion. So in this case, we have 2 atoms that are 0 because carbon is also have a formal charge of 0. And we have 2 oxygen atoms that have a -1 charge. So that is our best structure because that satisfies the rules there. Yep, as long as it's minimized, it's happy. And then we just want to make sure that if we have a negative charge, it goes on our most electronegative atom. And so since oxygen is more electronegative than carbon, then it's happy with the oxygen having the minus charge. Not values, but you can determine the trend for like these type of scenarios. Yep. Yes.
Where do the 2 extra electrons go to?
So they are included within like the valence electrons and the bonding electrons for the whole structure.
Okay, so they are not like inside the.
No, you can't like pick one and say, oh, that's my extra valence electron that I have. It's just included to the amount of electrons that you can use in your Lewis structure.
Okay.
Right, like I can't say this one right here is that extra one that I added, right? They're all kind of distributed around. Does that make sense?
Yeah, so if you have like, if oxygen has like 4 valence electrons originally. Like how do you, I'm just a little confused, like on how electrons move from like atoms,
Yeah, so right on the periodic table, carbon will have 4 valence electrons and oxygen will have 6 valence electrons. So kind of consider it like a potluck, right? Where you're going to show up, carbon shows up with its 4 electrons and it puts it in a pool. And then oxygen shows up with its 6 valence electrons and puts it in a pool. So they all start off with 0 and then they take what they need, right? So you pool all of your valence electrons together first and we see that we have 24. And now the different atoms will take what they want in order to complete their octet.
Okay,
Okay, does that make sense?
okay, and what order is followed, like?
Yep, so you're gonna draw your skeletal structure first. You're gonna give your electrons to the terminal atoms on the outside first, and then give it to the central atom.
Okay,
Okay, does that help?
yeah, so like the central atom is the last one.
Yes, yep,
Okay,
yep, it's gonna bond with lines first, and then you're gonna do your dots on the terminal, and then you can put any remaining on the central atom.
okay,
Yep.
thank you.
Alrighty. I have more questions for you. So we said that there were 3 total resonance structures. How many sigma bonds are in this structure? In a single structure? And where are they? Good, so there's 3 total sigma bonds. And that's gonna be a single bond. All single bonds are sigma bonds. And then in a double or triple bond, the first bond is always gonna be a sigma bond. So we have this one, and this one are all sigma. How many pi bonds do we have? We have 1 pi bond. What's the shape of this structure? I guess, what's the electron domain geometry? What is your molecular geometry? Also trigonal planar. What is our bond angle? Mhm. What is our bond order for the overall structure? What'd you say? Or 1.33. So your bond order is determined by how many bonds you have. So how many total like lines did we draw for our structure? There's 4. How many positions can we put the odd man out? 3, right? If we had something where it was, I'm just gonna use X's and Y's. Right, in this case, how many bonds did we draw? So I guess for the X and Y one. There's 5. Yep. How many different places can we put the odd man out? 3. So it would be 5 over 3 or 1.66. So in this case, this is 1.67. Okay, so you can rank these, right? We would say that your carbon-carbon right, if we're doing bond length, your carbon-carbon bond length is going to be less than your carbon-oxygen, then less than your XY, which is less than an oxygen-oxygen double bond. Yep.
How did you determine bond length?
So we know that your bond length for single bond is going to be the longest, and then your triple bond is going to be the shortest. And we're saying that for our CO bond and our CO2 or CO3 2 minus has a bond order of 1.33. So it has like a 1.33 bond length characteristic. So it's going to be a little bit shorter than a double bond, but a little bit shorter than a single bond, but a little bit longer than a double bond. Right. And then, so we know that like 1, if we're looking at a number line, this would be 1 and 2. So we're going to put 1.33 here and 1.67 here. Because your XY bonds that we drew have a little bit more double bond characteristic than single bond characteristic.
Okay.
Yes.
So bond length also is like
Yep.
bigger the thing.
Yes.
And double bonds.
Yes.
Why isn't a double bond bigger?
So oxygen is actually smaller than your carbon. Yep. So, right, that is, will be smaller and then they will get closer because it's a double bond. And so, right, the best way to look at it is saying we have a carbon, carbon, a carbon, carbon, and carbon, carbon, right? All of these are the same elements, and so their radii are the same, but as you go from 1, 2, and 3, our length is getting shorter. Between them. Does that help? Yes.
Get stronger as more.
Ye- Yep, think of it as like a taekwondo board, right? You have to break through each of the bonds in order to break it. So with a triple bond, you have 3 boards you have to break through before it splits, whether the single bond is just 1.
When does it deviate from the acceptance?
Third row or third period and higher. So, any element in third period and below can expand its octet. So carbon cannot expand its octet. It can only ever have 8, but phosphorus, sulfur, bromine, chlorine, iodine, all of those can expand its octet. Selenium is a good one that we see a lot. All of those can expand their octets.
And when is it less than?
Less than 8. Can anyone tell me when it's less than 8? There's 3. Hydrogen, beryllium, and boron. Perfect.
Do noble gases have any restrictions in optics?
Noble gases we don't usually just work with because they're already have a full octet of 8, and so they don't usually react with anything.
Oh, okay.
Yes.
So, the ones that can expand its octet, is it still technically following the octet?
Yes, so like when you're going through your steps of a Lewis structure and you're like, everything has an octet. As long as it's in the third period or below, and if it has 10 or 12, then it's still considered correct. Because it's allowed to do that. Yeah. Right, you're gonna check for your octet and you're like, oh, I have 2 more electrons left over and I can't make double bonds. You can slap them onto the central atom. Is that your question? Yep. Right, you only put them on, so you only make double bonds or triple bonds when you have not satisfied your octet and ran out of electrons, right? In our case up here, we had run out of electrons. There was nothing that we could put onto our carbon in order to make it have a full octet. So that's why we had to take one that was on the terminal atom and make a bond with it. But sometimes you're going to fill all of the octets of your terminal atom and still have 4 left over, and you're like, and that's when you slap them on the central atom. Okay. Yes.
So we already know hydrogen, it's like less than 8.
Yep.
Boron and beryllium.
Mhm.
Like, are those the only 3 ones that has less than 8?
Mhm.
So no more.
Nope.
Okay.
Nope, everything else will make 8. Boron will make 3 bonds and have 6 electrons, and beryllium will make 4 bonds and have, oh, I'm sorry, not 4 bonds. Will make 2 bonds and have 4 electrons. Great questions. Anything else? just like the Vesper theory, that whole thing. Yep. Yep. So when we talk about, right, Vesper, is that what you're talking about? Yep. So this is going to be your, molecule shape. So when we look at a certain, right, we look at all of our molecules, all of our ions that we talk about, they can be drawn spatially, right, three-dimensionally, so that we can visualize how their chemistry is going to work. This is just giving you a visual representation of that specific ion or molecule, whatever you're working with. So this gets broken down into electron domain geometry. And this is going to be based off of the number of bonds and lone pairs your central atom has. Right, all of this is based off of that central atom. And it comes from drawing your Lewis structure. So you want to make sure you have the best Lewis structure, because then you can answer all of these questions about the shape of your molecule. Okay, if we have electron domain geometries, how many different electron domain geometries do we have? There's 5, right? We can have an electron domain geometry of 2, 3, 4, 5, or 6. There's many, many examples. Right, this could be CO2. We can have NH3. I'm sorry, not NH3. BF3. We can have H2O. We can have PCl5. Or we can have, oh, I don't know. I think this is the correct one. Or SEF4. I believe that's the correct Lewis structure. Right, so in this case, around the central atom, there's going to be 2, 3, 4, 5, or 6 electron domains. Bless you. All right, for CO2, we have the bond to carbon oxygen on both sides. This is going to be an electron domain, and this is going to be an electron domain. It's wherever there's electron density, whether that's as a bond or whether that's as a lone pair. Okay, so you can kind of convince yourself for all of these that there's 2, 3, 4, 5, 6 for all of them. Each of these is considered to be, like, I call it, or I almost think of it as like an umbrella term, right? Because that's going to be the basis for your molecular domain geometry. Electron domain is like the skeletal structure of it. Molecular geometry is going to be the actual shape of your atom. Okay, molecular geometry, there's more that come in, or that more that come into play, right? We have bent for both trigonal planar and tetrahedral. We can have, you know, seesaw, everyone loves. We can have square planar, square pyramidal is a good one. Right, there's a whole bunch of whatnots and things that we can talk about in terms of shapes. Those are ones that you just have to memorize. I think visually they do a good job of representing what the actual shape is, right? trigonal bipyramidal, right, for 5 does look like 2 triangles with a triangle base. Right, 2 pyramids stacked together. Tetrahedral, you can just think about that visually of what a tetrahedral looks like. But I think of that always as like a tripod with something up top. So there's a lot of different ways that you can memorize these shapes, but those are something that you need to know. With all of these does come bond angles and how far away those can be away from each other, because the whole point about this is that they're in these shapes to minimize electron repulsion, right? All of your terminal atoms here have some sort of negative charge. Negative like charges will repel each other. And so in all of these different scenarios and all of the shapes that you are put on and decide your molecule is, have the minimum amount of repulsion for all of them. So key things to remember here is that lone pairs take up more space than bonds. So when we look at oxygen, if we look at H2O and then specifically the oxygen, there's 2 sets of lone pairs on that oxygen. And so usually the tetrahedral is going to have what bond angle between everything? What's the bond angle for a tetrahedral? 109.5. But now those lone pairs are going to take up more space. So they're going to smush that bond angle a little bit more. So that bond angle for water here is going to be less than 109.5. It's actually going to be like 104. Right, so the whole point here is that as you look at the molecular geometry and you get more specific on the actual shape, your bond angles are going to change a little bit for that one. Still minimizing repulsion. Does that help a little bit? Any other questions? Yeah.
For Lewis dot structures, is there a possibility where like one electron is left like alone?
There is a chance where it would be like a radical, we call that when it's left alone. But I think for the quiz and for the exam, I don't think you need to worry about that.
Okay.
Yeah. If you do, I apologize for giving you false information, but I think you just would rather, I would rather you worry about expanding the octet and then like beryllium or boron having 4 or 6 bonds or 4 or 6 electrons.
Okay.
Yep.
Thank you.
It does exist though. There are a whole bunch of radical chemistry that you can do. Anything else?
How do you determine if the molecule is like polar or non-polar if you're given the 2 electrical negativities?
Awesome. So you want to look at the shape that you're looking at. So I'm going to just take water because that's easy. Right. So if you're given electronegativities, which one is going to be more electronegative here? So oxygen is actually going to be more electronegative. Oxygen is closer to fluorine, so that one's going to be more electronegative. So if there, first of all, is a difference in electronegativity, which we do here because we're not being bonded to the same element, we're going to draw a dipole. We draw that towards the more electronegative element. So that's going to be towards oxygen here, right? And that's for both bonds. Both of them are a polar bond. This looks like it would cancel out, right? Because our 2 sideways are going to point in towards each other. But we know that this is actually a 3D shape, right? This is actually a bent structure. It comes from a tetrahedral. So that would be like saying that, right, I have my tripod for the tetrahedral and something up here. We'll say that these 2 are the lone pairs. So now the lone pairs push this together, and now that's going to push it upwards instead, right? Our vectors are saying these are going to cancel out, but we still have these upward momentums that we're using. And so our overall dipole is going up, right? So it's all based off of the shape of the structure and where lone pairs are and how they cancel out with those dipoles. Okay. Any other questions? Okay, it's 6:37, so I guess we'll wrap it up here. This will be recorded and posted, for when everything is done and whatnot. And then I'll put out probably a Zoom link on Friday, or maybe I guess tomorrow, since there's technically no classes on Friday. But I'll put out a Zoom link tomorrow, and it'll probably be Monday at 7 for a Zoom review session for anyone that would like to join, and ask your questions before the exam. Yay,
The review will be Monday.
I think Monday. Bachelor is over, so I have nothing else to do on Mondays anymore.
You should make them as, you should make that holidays or something. I would,
Do one session.
Okay,
we should have done something.
maybe I'll do that for the last couple of weeks or so.
Is it some sessions?
Yeah, I think Monday's winning, so probably Monday at 7 would be my guess. Yeah.
So you'd still consider oxygen the electro, or not, the central atom?
Yes.
Okay, because there's only one.
Yes, yep,
Okay.
and it's like, right, hydrogen's on the outside,
Uh-huh.
so as long, if there's 3, then there's gonna be some sort of central atom.
Okay.
So even in like carbon dioxide, like carbon would be the central atom
Okay,
here.
even if like oxygen is like less electronegative?
Yes, yep,
Okay.
yep.
Okay.
Do
Thank
the
you.
lab test will be posted?
It should hopefully be tonight, I think, for Dr. Altamos's class. And then Dr. Altman's maybe tomorrow, if it's not up tonight. Yep.
Thank you.
Yeah, thank you. Good luck. Yes. Admissible. That's a good question. I mean. Okay, so that's like, the ability to make a homogeneous solution. So if you think about salad dressing, oil and water are immiscible.
Yeah.
So if it's miscible, that means that you can like shake it up and it would stay shaken. Immiscible is like you would shake up salad dressing, but it's eventually gonna separate. So you can't make a homogeneous mixture. Does that make sense? Okay, awesome.
I have one more, sorry.
Yeah, yeah, no problem.
Cause like I'm supposed to learn the difference between ionic and covalent bonds. Like how will you explain that? So like I'm trying to look at videos and kind of like a little bit confused.
Yeah, so ionic bonds are going to be the transfer of electrons.
Okay, so it's just like one has one negative, one like positive.
Yep, right, because it's an ionic bond, so you have 2 ions. So think metal, not metal.
Yeah.
Yep, and then covalent is gonna be anything to nonmetals. So, right, a lot of like the upper right corner of the periodic table is covalent chemistry or non-metal to non-metal interactions.
Okay, so like it's like cations.
Yes, yep,
Okay.
yep, perfect.
All right, thank you.
Yeah,
Appreciate it.
absolutely. Have a great day.